So let's start talking about magnets. So in this video, we're going to talk about just magnetic interactions and then basic ideas about the magnetic field produced by things such as a bar magnet. So this is a bar magnet, and the ones that we'll be using in class are cylindrical, but it's the same concept. So it doesn't, just because it's called a bar magnet, it doesn't mean it has to look like a bar. And then it's marked with two poles. Let me switch back, you can't see that. So we have this pole and this pole. These are the poles of the magnet. And they're indicated with a letter here, so this would be the North Pole. I know you guys already kind of know this, so we're just reviewing. And the South Pole. And these are, the names for these, it's just kind of historical, goes back to China. When you suspend a bar magnet, you know, like from a thread, then it rotates, and this pole over here that we call north always points in the northern direction. So that's how it got its name. So that indicates the north direction, geographic north. Okay, so what happens when we start putting magnets together? So I'm going to draw a couple. So if we have a north-south and another north-south like this, then these things are going to attract each other. So we're going to have a pull towards each other because they're opposite poles. And so opposite attract, opposite attract. And if I flip it, you should already know this. So I have north-south and then south-north. These will repel. So these will be pushed away. So same, repel. So it's like electrostatics as far as like how the force will act. So like forces will attract, opposite, or like forces will repel, opposite will attract. And then what I want to do is I want to consider this case right here. So if we actually brought these two together, I would end up basically with a big magnet like this. So I'd have north, and then here I would have south, and then I would have north, and then I would have south. So basically I get a single magnet. Now this thing was made of two magnets, so you can see I have a north pole and a south pole. We don't really care about the middle, they're stuck together. And so this would operate just like an oversized bar magnet. And I can break this back into the two pieces, call it north-south, and I can break it over here into north-south. Now my question is, what happens if I break these? So now I'm back to my original two magnets, and I want to cut these things in half. So if I cut them in half, what do you think is going to happen? Well, basically, we would end up, it's not to scale, but you would get two new magnets, both with north-south poles. And over here you would get the same. So I'd have north-south, and that should be the other way around, north-south. Let's just fix that. So north-south and north-south, like that. So, and I could keep doing that. If I split it again, I would get another one, and it would always be north-south. We wouldn't ever be able to split this up so that I only have one pole. So there's no monopole magnets. That means a single pole, or at least we haven't found one yet. Scientists are looking for this actively. They're trying to, I just read an article, maybe I'll share it with you, and it was talking about how we might be able to produce one, but they've been searching for the existence of a monopole magnet and haven't found one. So if you take a magnet, cut it in half, it always produces a new magnet, a new dipole. Dipole. So it's always dipole. Okay, so it's similar to a charge. You know, if we have a charged rod, then we would end up with a negative and positive. And so this is a dipole. So this is always a dipole. Magnets are always dipoles. And You might think that it's similar to electricity, but it's not. Well, I'll come back to that. Because the other thing I want to talk about is this north direction. So let's suppose I had a compass needle. I'm going to draw it like this. This is a terrible drawing. And then what we do is we usually coat the side that is the north end. So it points north. So this would be the south end. So then my question is, which pole is this being attracted to? Because what it does is it swivels until it points. So it's attracted in this direction. And looking at, well, opposites attract, and this is the North Pole, it has to be attracted to a South Pole. So what that means is that on the Earth, our geographic north, geo-north, which is the north up near the North Pole or at the North Pole, is actually the magnetic South Pole. This isn't critical to understand, but it's true. So this is the North Pole of a compass points to the South Pole of the Earth, but that happens to be the geographic north. What we call north is actually magnetic south. Okay, know that it also depends on separation. I think you already kind of know that. If magnets are very far apart, there's not a lot of force between them. But then, so I was talking a little bit about electricity. If you have a charged object, so say I have a magnet and I take an uncharged, like styrofoam ball. So it's uncharged. If I bring the magnet near it, there's no attraction. Magnets attract iron. So there's no attraction. However, if I charge this thing up, so if I put an excess charge on it and I pull it close, it's going to be attracted to it. And so some that might lead some to think that magnetism is because of electrical charge, but it's not, because you know electric statics, and you know that charged objects attract neutral objects, which is the case here. So it has to do with the electrons in here that create the force. So magnets are not electric. Magnets are not electrostatics. And you need to know that distinction. It's not the same. Because we're actually going to tie magnetism to electricity, but it's different. It's not the magnet itself that comes. So anyway, they're different. So how does a magnet actually attract things? Let me just clear this. So you have this magnet. A north-south. And you put a little piece of, like a paper clip here. So you put a paper clip and then you let it go. This thing is going to move towards the magnet. Now the question is how? Because the magnet doesn't reach out and grab it. And so we should be familiar with this from electricity and from gravity. The magnet actually generates a field out here. And the field, which is called a B field. So the field out here, where this paper clip is, the field actually produces a force on the magnet and pushes it in. So it's a force of the B field that's going to push this in. So the magnet creates a field, and the field affects the paper clip. We've talked about this before with electrostatics. If you have a charge, if you remember, like the Van de Graaff, if we put a big charge on, I'm putting positives, but it's negatives. But if you put a big charge on it, it creates a field, an electric field, an E field around it. And then if I put another charge in there, that the field is going to produce a force on that object. And so later we'll talk about how we can actually measure the strength of the field and that sort of thing. But now we're doing a qualitative kind of, what do the fields look like? So I'm going to pull some pictures and show you, like for a bar magnet, a couple bar magnets, and what the field looks like. Because we can actually do it. You'll do it in lab. If you take a bunch of iron filings and you shake them around, all the iron filings, because of the force being produced, will line up according to the field. So let's look at some pictures. So here we're looking at a couple situations with bar magnets in order to understand the field that they create. Again, you'll do this in lab. So just a regular bar magnet, the lines indicate it's like equipotential. So these are field lines, and they'll run from north to south. So the arrows indicate the direction of the field. So all the field lines will begin at a north end and wrap around and go to a south end. Even these that kind of seem to disappear, they're going to wrap all the way around like that and so forth. So you'll get this wrapping around. Now, if we put two like ends or opposite ends together, these are going to attract. And so if we see, we'll see the same kind of motion with the field lines. They leave a north and go over to a south. I don't have a pen. Where's my pen? So the direction of the B fields, oh, I'm back behind it. The direction of the B fields is from north to south. Let me fix this real quick. Okay. So they go like this, in this direction, from north to south. Now in between, because these are opposite ends, the field lines go across. And so we actually get a pretty strong field. Remember, these are iso lines. So where they're tighter together, we're going to get more force. So we get more magnetic force right here between the two poles. Whereas when we have like poles, this one right here, I don't know about that. I don't know if I agree with that. These pictures I just pulled off the internet real quick. But basically what happens is when you pull these together, they're going to push and bend away. So you see how this one gets pushed, this field line gets pushed away from this one. So these will wrap back around, and you kind of have a dead space in there where it'll balance out. So what does the field of the Earth look like? So I'm going to show you one. I'm going to show you two pictures. We're going to look at this one. And I want you to find what's wrong with this picture. And I took this from livescience.com. So what's wrong with it? Well, unless they used it in, I'm just noticing that it says Earth magnetic field reversal. But this right here, right? This is wrong. For our current state, oh, I guess they are showing if it flips, because this is the positive. All right, so maybe they're okay. That should... But for our field right now, this is the south magnetic field and the north geographic pole. So this is our south pole up here. And you can see the field lines leave and go from north into the south, just like they do on a big bar magnet. So this picture, I have problems with it. However, it doesn't look like this because it's being bombarded by electromagnetic radiation from the sun. And so it gets distorted. And so this is kind of a graphic that shows that. So it gets crunched on one side and then it gets elongated on the other side. And if it weren't for the magnetic field, we would be dead. We wouldn't be here because these rays would come in and bombard the Earth and fry everything up. So the magnetic field protects us. It gives us a nice cushion against the electromagnetic radiation off of the sun. So that's the basic fields. Being able to draw them is pretty important, knowing that they go from, they always go from the North Pole to the South Pole, and that's magnetic. So knowing this picture, actually all three of these, kind of how they lay out. Okay, so the last thing is current carrying wire. So current carrying wire also produces a magnetic field. Let me clear all this stuff. So if we have a wire like so, I'm just going to exaggerate. Or you know what, let's not do that. Just a wire. And I attach it to a current such that the current is moving in this direction. So the current's moving along the wire. Then the wire itself is going to produce a magnetic field. And if I put a compass underneath the wire, so let me write under because I'm not going to be able to draw it. So if it's under, then the compass would point in this direction. That would be underneath. And if I put it on top, it's going to point in this direction, on top. And remember, a compass always points into the field. That's the way we say it, or it's the way I say it. It points into the field, which means it points to the South Pole. So it points along, so recall what we just said, north, south. Fields go from north to south. So the compass always points along the field lines. So looking at this, if it's under and it goes this way, and then it's on top and it goes this way, then what it does is it makes a circle around the wire. And that's exactly what it does. So it goes this way. It makes a circular B field. All right, so what happens if I reverse the current? So if the current goes this way, then it's going to flip everything. So then when I put the compass on top, now it's going to point up, and on bottom it's going to point down if it's underneath. And so the B field is going to rotate this direction, or rather it's going to go this way. And we could show that with a compass. You'll do this in lab. So basically what this does is it follows the right-hand rule. So let me get a picture. So this is our right-hand rule, and basically what you do is you point your thumb in the direction of the current, and then you curl your fingers, and that's going to tell you the direction of the field. So for this one, the current's moving up, so you point your thumb up, so your fingers would curl around the wire in this direction as shown in the picture. So the B field is like that. So if you're going this way, you point your thumb. So hold your hand in front of your face and point it to the left, and you'll see that when you curl your fingers, it would go around the wire. Whereas the one down here, you would point your thumb to the, the top one was thumb to the right. On the bottom, it's thumb to the left because that's the direction of the current. So you see it curls over and then comes back under. So anyway, that's the right-hand rule for the direction of the B field. And so we can combine that into a loop. And so let's imagine that we have some some potential, a battery source hooked up to a wire and a resistor, of course, because we always have resistors. And then it comes down, and then what we're going to do is we're going to actually coil the wire. So we have a big coil of wire. And then it comes out. We're going to study this a lot more. So this is just kind of a qualitative. So when I draw this, I can see that the current is going to come this direction. So when it comes in here, it's going this way. So we can think about the B field across here. So since it's going this way, you would point, I can't draw a hand. All right, there you go. So you would point your thumb this way, so your fingers would curl this way, so it's going to wrap around this direction. And it's going to do the same thing over here. It would go around the wire. Over here, you would have to point your thumb down. So it's going to wrap like this. Okay, so what's going on inside of here? I'm gonna expand it so that I can draw. So the wire comes like that, and then it kind of wraps and coils. Okay, so we don't care. I just care about right here. So think the current's coming this way, and then it comes across right here. So what you can see is that the current is moving this way here, and then it comes around over here, and it's moving this way. So on the top, your thumb would go left, and so it's going to come... I think I have this wrapped wrong. No, yeah. No, it's fine. It doesn't matter. So on the top, it's going to go this way, and it's going to come out through here. And on the bottom, your thumb would go left, and then it would curl, and it's going to come back out through the middle, like this. So both of these, on the top and the bottom, come through the middle. So what it ends up doing, I'm going to draw it sideways. If we have all of these coils, is the B fields add up in the middle, and we get a really strong B field right through the center of the coil. And this is how we make electromagnets. So we coil it up, and we'll learn it depends on the number of coils and the radius of the turns and all of this stuff. But this will generate a very strong B field inside of it. So anyway, we'll come back to that. Again, this is all qualitative. But it makes me think about another thing that you're going to need to know, and you might as well start thinking about it now. What happens if I have two wires next to each other, so parallel wires, and let's say the current is moving in the same direction. So the current's going here, current's going here. So what we want to think about is what's the B field in between them. So since it's going up, it's going to curl around in this direction. And over here, since it's going up, it's going to curl around in this direction. So you can see that this piece and this piece, they're going in opposite directions. So right in the middle, we would probably have 0 B field. They would cancel each other out. But you would get more on this side and you would get more on this side than you would with a single wire. So we'll do this type of analysis as well. But that kind of covers the basics. That's enough information for now.